Okay, it's materials engineering project presentation. The material investigated here is aluminum 661 alloy composite with silicon carbide coated carbon nanotubes. Usage of aluminum increased in the second half of the 20th century. Pure aluminum is hard to obtain from bauxite. With the advancement in the purification process, aluminum has become more abundant in daily life. Due to its low weight, aluminum is widely used as matrix material in composites. Weight reduction is important in transportation industry to reduce fuel consumption. Some examples of aluminum silicon carbide usage in automobiles are pistons, brake rotors, and drive shafts. Among ceramic reinforcements, silicon carbide is widely used due to its high hardness and mechanical strength. In the figure, you can see the fabrication of silicon carbide nanotubes. CNT is coated with iron first. Iron nanoparticles on the surface of CNTs aid the chemical reaction between silicon oxide gas and carbon. Carbon dioxide forms in this reaction, which is carried away by argon gas flow. Silicon dioxide is formed as a layer on the outermost surface of the nanotube. This layer enhances the interfacial bond strength between the aluminum 661 matrix and silicon carbide carbon nanotubes. It also prevents the reaction between aluminum and silicon carbide, hence the formation of aluminum carbide, which is a brittle material. As seen in the figure, silicon carbide carbon nanotubes are at the grains and grain boundaries. Here, as the percent volume of silicon carbide carbon nanotube increases, tensile strength of the material increases. For the 5% volume of silicon carbide, tensile strength increases approximately 38% in comparison with pure aluminum alloy. There is 58% increase in Young modulus from 7.2 to 110.8 gigapascals, and there is a 62-point increase in Vickers hardness from 55.1 to 89.6 for the 5% volume silicon carbide, but there is a 46% decrease in elongation, hence ductility. The elongation is 33.5 in pure aluminum alloy and 18.1 in the composite. Decrease in the friction coefficient results decrease in specific wear rate. As the volume percentage of silicon carbide increases, the friction coefficient decreases and the specific wear rate decreases. In this figure, wear surfaces of pure aluminum alloy and 5 volume percent silicon carbide aluminum 661 is observed. A and B is the pure aluminum alloy, C and D is the composite. For pure aluminum, large portions of material are removed by periodic delamination fractures during plastic deformation, as seen here. In silicon carbide nanocomposite, surface presents improved wear properties. Debris particles, these particles, are uniformly distributed and acts as hard abrasive particles with limiting material loss. Furthermore, no delamination is observed. Wear mechanism of the composite is predominantly abrasive, whereas pure aluminum alloy shows delamination and deformation. Overall, improved mechanical and tribological properties indicates the possibility of aluminum 661 silicon carbide carbon nanotube use in structural and wear applications in heavy-duty conditions. Thank you for watching.